The authors establish the weak maximum principle for finite element methods applied to parabolic equations in two-dimensional general polygonal domains and three-dimensional convex polyhedral domains. This principle is proved for both semi-discretization in space and fully discrete methods utilizing k-step backward differentiation formulae for k equals 1, 6. The semi-discrete result is obtained through a dyadic decomposition argument and local energy estimates, which enable the handling of non-smooth domain boundaries. This approach is particularly useful in two-dimensional settings, where the discrete maximum principle for elliptic equations is typically limited to piecewise linear elements. In contrast, quadratic elements require uniform equilateral triangulation. In three-dimensional settings, the scenario becomes more complex, and ensuring the discrete maximum principle for elliptic equations is challenging. However, the author's approach provides a way to circumvent these difficulties. The fully discrete result for multi-step backward differentiation formulae is proved by utilizing the solution representation via the discrete Laplace transform and resolvent estimates. These estimates are inspired by the analysis of convolutional quadrature for parabolic and fractional-order partial differential equations. The weak maximum principle is a fundamental tool for studying elliptic and parabolic partial differential equations. The discrete counterpart of this principle, associated with finite element methods, has a well-established history of research and remains an active field. The author's contribution lies in providing a unified approach to prove the weak maximum principle for parabolic equations in polygonal domains. This has significant implications for the numerical analysis of partial differential equations, as the discrete maximum principle is not an inherent property and is heavily influenced by the triangulation of the physical domain. The author's approach offers a way to overcome the challenges associated with non-smooth domain boundaries and provides a foundation for further research in this area. This section delves into the weak maximum principle of semi-discrete and fully discrete finite element methods, FEMs, for the parabolic equation. It aims to determine if the semi-discrete and fully discrete finite element solutions of the given equation are uniformly bounded by constant multiples of the norms of the initial and boundary values. The authors build upon existing results for elliptic problems and explore the parabolic equation partial differential to increment u equals 0 in 0, infinity, times omega, with specified initial and boundary conditions. Previous works on the discrete maximum principle for fully discrete FEMs, such as those by Fuji, required specific families of acute triangulations and lower bounds for the time step size, but these results did not extend to semi-discrete FEM. Recent studies, however, demonstrated the necessity of the mass lumping method for semi-discrete FEM, without which the strong discrete maximum principle does not hold, even for acute triangulation. To fill a knowledge gap, the current paper investigates the weak discrete maximum principle of semi-discrete FEM for parabolic equations. A connection to existing research is made, particularly the equivalence between the weak maximum principle and the uniform boundedness of the finite element heat semigroup in L infinity, omega, previously proven for smooth domains with curved simplices fitting the boundary geometry. A more recent solution extended to non-smooth domains and presented technical challenges in handling domain non-smoothness and elliptic regularity. This section provides context to and advances our understanding of semi-discrete and fully discrete FEM solutions. The paper investigates the weak maximum principle of time discretizations with respect to the boundary value, a previously unexplored topic. Specifically, it examines the stability of k-step BDF methods with k ranging from 1 to 6, considering the challenges posed by boundary data, non-smooth domains, and the lack of astability for k-step BDF with 3 is less than or equal to k is less than or equal to 6. The analysis focuses on two main points. First, it seeks to prove the error estimate, a nabla dl gamma h minus gamma, a nabla dl L1, 0, infinity. L1, dh, is less than or equal to h, where dh denotes the set of points within a distance h from the boundary of the domain omega, and gamma h are the parabolic Green's functions with respect to the regularized delta function, delta, and the discrete delta function delta h, respectively. This error estimate is not straightforward due to the lack of an approximation property for the initial value gamma h, 0, minus gamma, 0, in the error equation. To overcome this challenge, the authors leverage the local Holder's inequality, the smoothing property of the discrete heat semigroup, and the lower bound alpha greater than 1/2, where alpha is the indicator of the domain's smoothness. The lower bound 1/2 is sharp in the sense that the proof does not work if alpha less than 1/2. Second, the paper establishes the weak maximum principle of time discretizations by studying the representation formula of UN in terms of the generating functions U, zeta, equals n airy summation infinity sin n equals kun, which can be understood as the discrete Laplace transform or Z transform of the fully discrete finite element solution. However, a direct application of the L infinity norm to the representation formula of UN introduces a logarithmic factor, which emerges from the summation process. To eliminate this logarithmic factor, the authors compare the representation formulas of the discrete and continuous Laplace transforms, necessitating the development of consistency between these two types of Laplace transform. A central correspondence relation concerning the boundary data is stated in Lemma 5.4, gh, z, equals E minus tau z plus E tau z minus 2, z tau gh, E minus tau z, which plays a crucial role in the analysis. The author's approach involves establishing a connection between the discrete and continuous Laplace transforms, allowing them to eliminate the logarithmic factor and prove the weak maximum principle. This is achieved through the development of a consistency relation between the two types of Laplace transform, as stated in Lemma 5.4. The paper's findings have significant implications for the stability and accuracy of time discretizations in numerical simulations. The discrete Laplace transform plays a crucial role in ensuring the consistency of solution maps associated with the backward difference formulas, BDF1 and BDFK. However, it is revealed that BDFK exhibits instability for 3 is less than or equal to k is less than or equal to 6, necessitating the use of the BDF1 symbol within the resolvent operator to maintain stability. This paper presents two primary theorems: the weak maximum principle for semi-discrete and fully discrete finite element methods, FEMs, in parabolic equations. To establish these theorems, the authors introduce necessary notation and derive the weak discrete maximum principle of the semi-discrete FEM. The weak maximum principle is a fundamental concept in numerical analysis, ensuring that the discrete solution satisfies a maximum principle, analogous to the continuous problem. The semi-discrete and fully discrete FEMs are discretization methods used to approximate solutions of parabolic partial differential equations. The paper concludes by discussing the potential extension of the results to discontinuous Galerkin timestepping methods, which can accommodate highly variable time step sizes. However, the authors acknowledge the limitations of the current approach and suggest that novel approaches, such as those developed recently, may offer potential solutions to overcome these limitations. The BDFK method is a timestepping method used in the finite element method, FEM, for solving partial differential equations. This method is a theta k stable, meaning that the set Z element of C0 arg Z less than theta k is contained in the stability region of the method. The stability angle theta k depends on the value of k, with theta k equals 90 degrees, 90 degrees, 86.03 degrees, 73.35 degrees, 51.84 degrees, and 17.84 degrees for k equals 1, 2, 3, 4, 5, and 6, respectively. The fully discrete FEM with BDFK timestepping method seeks to find h element of sh such that the following equation holds. 1. Tau sigma j equals 0 delta j hj vh plus nabla h nabla vh equals 0 for all vh element of sh n equals k n, where h equals gn_h on partial differential omega n equals k n. This equation is derived from the weak form of the underlying partial differential equation and the BDFK method. The second main result of this article is Theorem 2.2, which states that if omega is a polygon, possibly non-convex, in R² or a convex polyhedron in R³, then the fully discrete solution given by the above equation satisfies the weak maximum principle for R is greater than or equal to 1 in R² and R is greater than or equal to 2 in R³. This principle asserts that the maximum norm of the fully discrete solution is bounded by the maximum norm of the initial and boundary conditions. The proof of theorems 2.1 and 2.2 also reveals that for a convex polyhedron in R³ and finite elements of degree R equals 1, the semi-discrete and fully discrete FEMs satisfy the weak maximum principle with an additional logarithmic factor. This is expressed in equations 2.3 and 2.4. In addition to these results, the article provides notation, finite element discretization, and regularized Green's function. The notation includes conventional notations of Sobolev spaces W's, Q, omega, and abbreviations such as LQ equals W0, Q, omega, and H's equals W's, 2, omega. The Bachner norm is also defined for W's, Q-valued functions f. 0, t, right-pointing arrow W's, Q. The definition and properties of specific finite element spaces are crucial for the spacetime variational formulation of parabolic problems. A subdomain D within the larger domain omega is considered, and a spacetime variational norm for functions f on D is defined as a nabla DLF, a nabla DLWs, Q, D, where the infimum extends over all possible functions f defined on omega such that f equals f in D. A similar norm for functions on a spacetime subdomain Q within the larger spacetime domain Q equals 0, 1 times omega is denoted as a nabla DLF, a nabla DLLPWs, Q, Q, where the infimum extends over all possible functions f defined on Q such that f equals f in Q. L2 inner products on omega and spacetime L2 inner products on Qt equals 0, t, times omega are denoted as phi, phi, and u, v, respectively. The finite element spaces are constructed using a quasi-uniform triangulation of the domain omega, denoted by Shay, D, which is the space of functions of Shay restricted to the domain D. The subspace of Shay, D, consisting of functions that equal 0 outside D is denoted by S0H, D. Four key properties of the finite element spaces on a quasi-uniform triangulation of the domain omega are established. 1. Quasi-uniformity. For all triangles, or tetrahedron, tau h in the partition, the diameter h of tau h and the radius ρ of its inscribed ball satisfy k-1 h is less than or equal to ρ L is less than or equal to h L is less than or equal to kh. 2. Inverse inequality. If D is a union of elements in the partition, then a nabla DL chi, a nabla DL WL, P, D, is less than or equal to kh minus L minus k minus D, q minus D, P. A nabla DL chi, a nabla DL WK, Q, D, for all chi element of Shay. For 0 is less than or equal to k is less than or equal to L is less than or equal to 1 and 1 is less than or equal to q is less than or equal to p is less than or equal to infinity. 3. Local approximation and superapproximation. An operator IH. H1, 0, omega, right-pointing arrow Shay exists with the following properties. For V element of H1 plus alpha, omega, intersection H1, 0, omega, the estimate holds. A nabla DLV minus IHV, a nabla DLL2 plus H, a nabla DL nabla, V minus IHV. A nabla DLL2 is less than or equal to KH1 plus alpha, a nabla DLV, a nabla DLH1 plus alpha for all alpha element of 0, 1. If D is greater than or equal to 2H, the value of IHV in D depends only on the value of V in DD. If D is greater than or equal to 2H and V, subset of D, then IHV element of S0H, DD. If D is greater than or equal to 2H, omega equals 0 outside D, and partial differential BO is less than or equal to CD minus beta for all multi-index beta, then psi H element of Shay, DD, equals IH, ops H, element of S0H, DD, a nabla DL ops H minus IH, ops H, a nabla DLL2 plus H, a nabla DL ops H minus IH, ops H, a nabla DLH1 is less than or equal to KHD minus 1, a nabla DL psi H, a nabla DLL2, DD. If d is greater than or equal to 2h and omega is defined as 1 on dd, then IH, ops h, equals psi h on d. These properties of the finite element spaces are essential for the analysis and implementation of the spacetime variational formulation for parabolic problems, as they provide the necessary tools for approximating solutions and estimating errors. The paper delves into the properties of quasi-uniform triangulations and their role in finite element spaces. It emphasizes that these properties hold for globally continuous piecewise polynomials of degree r is greater than or equal to 1. The authors present local and global estimates for the interpolation operator IH and the L2 projection PH, as well as the Ritz projection RH. These estimates are crucial for understanding the approximation properties of these operators in the context of finite element methods. Furthermore, the paper introduces the concept of Green's functions for parabolic equations and their discrete counterparts. The discrete delta function delta h, x0 is shown to decay exponentially away from its center x0, which is an important property in numerical analysis. The Gaussian estimate for the Green's function g, t, x, y, is also mentioned, indicating its symmetry and analytic extension to the right half-plane. These results are significant because they provide a solid foundation for the development of numerical methods for solving partial differential equations, particularly in the context of finite element methods and their applications in various fields such as engineering, physics, and computer science. The Gaussian pointwise estimate for the time derivatives of Green's function is a crucial tool in establishing the weak maximum principle of semi-discrete finite element methods, FEM. By leveraging Cauchy's integral formula, the authors derive this estimate, which is essential for analyzing the regularized Green's function and its finite element approximation. The regularized Green's function is defined as the solution to a parabolic equation with a Dirac delta function as the initial condition. Its expression in terms of the Green's function enables the derivation of a Gaussian pointwise estimate, akin to that of the Green's function. This estimate plays a vital role in the subsequent analysis of semi-discrete FEM, particularly in establishing the weak maximum principle. To achieve this, the authors employ a technique based on dyadic decomposition and local energy estimates. The domain is partitioned into subdomains, and estimates of the finite element solutions are presented in each subdomain. The dyadic decomposition of the domain is introduced, with specific conditions set for the parameters involved to ensure the validity of the approach. The regularized Green's function is expressed as a solution to the parabolic equation. Partial differential u, partial differential t equals delta u plus delta xx. With the initial condition u, x, 0, equals delta xx. The Green's function is then defined as the fundamental solution to this equation. The Gaussian pointwise estimate is derived as u partial differential t, x, t, is less than or equal to c squared express, xx squared, for t, where c is a constant depending on the dimension and the order of the derivative. This estimate is crucial for the analysis of the semi-discrete FEM and the establishment of the weak maximum principle. The weak maximum principle is established through a two-part proof. The first part involves demonstrating the boundedness of the finite element solution, while the second part relies on the dyadic decomposition and local energy estimates. The authors present specific conditions for the parameters involved in the dyadic decomposition to ensure the validity of the approach. These conditions are essential for the establishment of the weak maximum principle and the analysis of the semi-discrete FEM. The authors introduce a series of definitions and notations crucial for the subsequent analysis, including sets and domains that partition the domain omega t and omega into smaller regions. Specifically, they define q asterisk operator, x0, omega asterisk operator, x0, qj, x0, omega j, x0, dj, x0, and their variations, which enable the establishment of a hierarchy of domains. The sets qj, x0, and omega j, x0, are defined as concentric annuli around x0, with qj, x0, being the intersection of omega t and the annulus. The sets dj, x0, are defined as balls centered at x0. Notations for the union of these sets, such as q0, x0, and omega 0, x0, are also introduced to simplify the notation. To measure the regularity of functions in the domains Q and D, the authors define several norms and seminorms, including a nabla DLV, a nabla DLK, V, K, Q, and V, K, D. These norms are essential for the analysis of the Green's function and its regularized version. A generic positive constant C, independent of H, x0, and C** operator, is also introduced and used throughout the paper. The finite element subspaces sh are used to discretize the domain omega, and 3 technical lemmas are presented, with the first 2 being proved in a previous work for general polyhedra. These lemmas provide estimates for the Green's function g and the regularized Green's function gamma in terms of the introduced norms. Specifically, the estimates are given as lemma 1. G, x, y, is less than or equal to c, v, k, q, x0, v, k, d, x0, lemma 2. Gamma, x, y, is less than or equal to c, v, k, q, x0, v, k, d, x0, lemma 3. G, k, q is less than or equal to c, v, k, q, x0, v, k, d, x0. These estimates are crucial for the subsequent analysis, as they establish the regularity of the Green's function and its regularized version. Estimation of fundamental solutions for elliptic and parabolic operators in domains with corners is a crucial problem in partial differential equations. This research paper presents a series of lemmas providing estimates for fundamental solutions and their derivatives in polyhedral domains in R⁻D, d equals 2, 3, and convex polyhedral domains in R³. These estimates are essential for understanding the behavior of solutions to elliptic and parabolic equations in such domains. The authors employ the energy method and elliptic regularity theory to derive estimates for the fundamental solutions of the Laplace operator and the heat operator. Specifically, they use the Sobolev embedding theorem and the stability of the Ritz projection to establish estimates for the fundamental solutions and their derivatives. These estimates are critical for studying the properties of solutions to elliptic and parabolic equations in domains with corners. The paper highlights the importance of understanding the behavior of fundamental solutions in domains with corners. This knowledge can be used to establish existence, uniqueness, and regularity results for solutions to elliptic and parabolic equations in such domains. The estimates provided in the lemmas can be applied to various problems in partial differential equations, including the study of diffusion and wave propagation in non-smooth domains. The estimates provided in the lemmas are based on a combination of mathematical tools, including the energy method, elliptic regularity theory, and the Sobolev embedding theorem. These tools allow the authors to derive precise estimates for the fundamental solutions and their derivatives, which are essential for understanding the behavior of solutions to elliptic and parabolic equations in domains with corners. The paper contributes to the development of mathematical tools for studying elliptic and parabolic equations in domains with corners, an important area of research in partial differential equations and their applications. The estimates provided in the lemmas can be used to establish existence, uniqueness, and regularity results for solutions to elliptic and parabolic equations in such domains, which is crucial for various applications in physics, engineering, and other fields. The authors present a proof sketch demonstrating the boundedness of the constant k, crucial for establishing the stability of the finite element method. By multiplying both sides of the inequality by h⁻1/2, the lowest powers of h in the consistency and stability parts of the proof are h⁻alpha and h⁻1 plus alpha d, 2, respectively, ensuring the stability of k. To simplify the problem, the authors introduce a notation system, defining gamma h, t, gamma, t, and f, t, as the Green's functions and their differences. They then consider the finite element solution of the parabolic problem and substitute Vh equals gamma h, street, into the variational form, yielding an expression for s, x0, in terms of the finite element solution Wh and the Green's function gamma h. By choosing Wh to be the finite element function that equals UHAT at interior nodes and 0 on the boundary, the authors derive an expression for s, x0, involving the finite element solution GH. which equals GH on the boundary and 0 at interior nodes. Restricting the domain of integration to dH, the region within a distance h from the boundary, further simplifies this expression. The authors then introduce the solution U of the parabolic PDE problem and utilize the maximum principle to bound the gradient of U. Testing the PDE equation with the Green's function gamma, street, and integrating the result yields an expression for U, S, delta x0, which will be used in subsequent analyses. This expression is critical for understanding the behavior of the finite element solution and its relationship to the underlying PDE problem. The proof sketch demonstrates the boundedness of K, ensuring the stability of the finite element method. The simplified notation and restricted domain of integration facilitate the derivation of key expressions, which are essential for further analysis. The maximum principle and Green's function are employed to bound the gradient of U and obtain the expression for U, S, delta x0, providing a foundation for subsequent investigations. Estimates for the solution of a parabolic equation are presented, focusing on the domain Q equals 0, 1 times omega with the restriction h less than 1, for C asterisk operator. The basic energy estimate is applied to derive bounds for various norms of the solution and its derivatives. The equation xj, ih phi minus phi, equals dj, partial differential t, ih phi minus phi, 1, q plus, partial differential t, ih phi minus phi, q plus d minus 1j, ih phi minus phi, 1, q plus d minus 2j, ih phi minus phi, q is used to estimate the norms of the solution and its derivatives. The estimates are presented in two parts. Part 1 concerns estimates for t element of 0, 1, and Part 2 concerns estimates for t is greater than or equal to 1, leveraging the smoothing property of parabolic equations. In Part 1, the basic energy estimate yields bounds for the L2 norms of the solution and its derivatives, including partial differential t gamma, partial differential t gamma h, nabla gamma h, partial differential t gamma, and partial differential t gamma h. These bounds are derived using equations 4.25 to 4.29, which involve the norms of the initial data gamma 0 and gamma h 0. The estimates are then used to bound the norms of the solution and its derivatives in the domain Q asterisk operator, a subset of Q. The bounds are presented in equation 4.30, which shows that the norms of the solution and its derivatives in Q asterisk operator are bounded by CD asterisk operator H1 minus D2. The volume of Qj is CD2 plus dj, and the solution and its derivatives are decomposed into two parts. One part is estimated in the domain Q asterisk operator intersection dth, and the other part is estimated in the domain Qj intersection dth. The estimates are then combined to derive a bound for the L1 norm of the solution and its derivatives in the domain dth, presented in equation 4.31, which shows that the L1 norm of the solution and its derivatives is bounded by cc5 plus d2 plus k. The constant k is defined in equation 4.32, which involves the norms of the solution and its derivatives in the domain Qj. Finally, by setting phi h equals gamma h, phi equals gamma, phi h, 0, equals ph delta x0, and phi 0 equals delta x0, and phi h equals partial differential t gamma h, phi equals partial differential t gamma, phi h 0 equals increment hph delta x0, and phi 0 equals increment delta x0. The constant k is estimated. Estimates and bounds for various terms involved in the analysis of a numerical method for solving partial differential equations are presented. These estimates are derived using a combination of local interpolation error estimates, exponential decay properties of a regularized Green's function, and bounds on the solution and its derivatives. The first two estimates, 4.33 and 4.34, bound the norms of the solution and its time derivative, respectively, in terms of the norms of the solution and its derivatives on a coarser mesh. These estimates involve constants that depend on the mesh size, the dimension of the problem, and the regularization parameter. The next four estimates, 4.35, 4.38, bound the norms of various terms involving the solution, its derivatives, and the interpolation operator. These estimates involve constants that depend on the mesh size, the dimension of the problem, and the regularization parameter, as well as the Holder exponent of the solution. The final estimate, 4.39, combines the previous estimates to bound the norm of the solution in terms of the norms of the solution and its derivatives on a coarser mesh. This estimate involves a constant that depends on the mesh size, the dimension of the problem, and the regularization parameter. Key concepts in this analysis include local interpolation error estimates, exponential decay properties of a regularized Green's function, and bounds on the solution and its derivatives. The Holder exponent, which measures the smoothness of a function, and the interpolation operator, which maps a function on a fine mesh to a function on a coarser mesh, are also crucial. The mathematical techniques employed in this section include functional analysis, particularly the use of norms and bounds to estimate the size of functions and their derivatives, as well as partial differential equations and numerical analysis. The purpose of these estimates and bounds is to establish a foundation for analyzing the numerical method, ultimately proving its convergence and stability, and providing error estimates for the solution. The authors establish an estimate for the quantity k, a crucial component in their analysis. By applying the Sobolev embedding theorem, they bound the Q-norm of f by the Q-norm, leveraging the assumption of a convex domain to choose alpha greater than 1. This leads to a series of inequalities involving various norms of f and its derivatives. The authors then draw on previously established estimates from their work in 21 to bound the norm f qj. This bound is expressed as a sum of two terms, one involving a power of h and another comprising a sum over I, featuring norms of f and its derivatives. Substituting these bounds into the initial inequality for k, the authors arrive at a final estimate for k. This estimate consists of several terms, each involving powers of h, norms of f and its derivatives, and sums over j. Critically, the authors demonstrate that this estimate can be controlled by judiciously selecting epsilon and c values, thereby completing their analysis of the bound for k. In the case of D equals 2 or D equals 3 with R is greater than or equal to 2 and a convex domain omega the authors establish an upper bound for K in terms of C, D, alpha, featuring F, chi and D. Specifically, they show that K is less than or equal to C plus CC3 plus D, 2 plus C where C is a constant that can be chosen large enough to absorb the term CKC alpha on the right-hand side of the inequality. This leads to the simplified bound K is less than or equal to C . The authors then proceed to part 2, where they consider the error equation for T element of 1. Infinity, They define a smooth cutoff function chi t, and use it to derive an equation for eta t equals chi t gamma h t gamma t . This equation can be written in the form of a discrete parabolic equation trh eta increment hrh eta equals partial differential t chi phrh gamma plus partial differential t chi t gamma h t ph gamma t with rh eta 0 equals 0 . The discrete Laplacian increment h is defined as minus increment hvh chi equals nabla vh nabla chi for all vh element of Shay . The author's goal is to establish an upper bound for the error h1, a nabla dl nabla f, a nabla dll1, 0, 1, times dh, which they achieve by substituting the bound k is less than or equal to c into equation 4.31, resulting in h1, a nabla dl nabla f, a nabla dll1, 0, 1 times dh is less than or equal to c . The solution to equation 4.48 can be expressed in terms of the semi-group at increment h, as shown in equation 4.50. By applying the operator minus increment h, 1/2 to both sides of this equality, we arrive at equation 4.51. This, in turn, yields an estimate for the norm of the gradient of RH eta, t, given by equation 4.52. This estimate relies on the exponential decay estimate for the discrete semigroup, provided in equation 4.53, and a smoothing estimate for the analytic semigroup at increment h. The significance of this estimate lies in its crucial role in the analysis of the discrete time problem, providing a fundamental component in the overall solution framework. The proof of theorem 2.1 is completed by establishing estimates 4.45 to 4.55, which imply 4.21. Specifically, by integrating the inequality for t element of 1 plus infinity, and using Fubini's theorem and equations 3.6 to 3.7, we obtain the estimate nabla d caret l nabla rh eta underscore d caret l l caret 1 plus infinity l squared is less than or equal to c nabla d caret l nabla phrh partial differential t chi underscore gamma underscore d caret l l caret 1 plus infinity l squared plus c nabla d caret l minus increment h caret minus 1 gamma h ph gamma underscore d caret l l caret 1 l squared. This estimate is further refined using lemma 4.3 to yield nabla d caret l nabla rh eta underscore d caret l l caret 1 plus infinity l squared is less than or equal to ch caret alpha nabla d caret l partial differential t chi underscore gamma underscore d caret l l caret 1 plus infinity h caret 1 plus alpha plus c nabla d caret l gamma h gamma underscore d caret l l caret 1 plus infinity l caret 1, which ultimately leads to the estimate nabla d caret l nabla rh eta underscore d caret l l caret 1 plus infinity l squared is less than or equal to ch caret 1/2. Furthermore, using the Poincaré inequality, we obtain nabla d caret l gamma hrh gamma underscore d caret l l caret 1 plus infinity h caret 1 omega is less than or equal to ch caret 1/2. By applying the triangle inequality, Holder's inequality on dh, equation 3.7 and lemma 4.3, item 1, we derive the estimate nabla d caret l gamma h gamma underscore d caret l l caret 1 plus infinity w caret 1 dh is less than or equal to ch caret 1/2. Nabla d caret l gamma hrh gamma underscore d caret l l caret 1 plus infinity h caret 1 dh plus ch caret 1/2. Nabla d caret l rh gamma gamma underscore d caret l l caret 1 plus infinity h caret 1 dh, which is further simplified to nabla d caret l gamma h gamma underscore d caret l l caret 1 plus infinity w caret 1 dh is less than or equal to ch. Moving on to the proof of theorem 2.2, we aim to establish the weak maximum principle of fully discrete Fem. To this end, we decompose the solution into three parts: u underscore n caret h equals u underscore n caret h, 1 plus u underscore n caret h, 2 plus u underscore n caret h, 3, where u underscore n caret h, 1, u underscore n caret h, 2, and u underscore n caret h, 3 are finite element solutions of problems 5.3, 5.4, and 5.5, respectively. These problems involve the finite element method for the heat equation with different boundary conditions and initial conditions. The goal is to show that nabla d caret l u underscore n caret h underscore d caret l l caret infinity omega is less than or equal to c max underscore 1 is less than or equal to n is less than or equal to k1 nabla d caret l u underscore n caret h underscore d caret l l caret infinity omega plus c max underscore k is less than or equal to n is less than or equal to n, nabla d caret lg underscore n caret h underscore d caret ll caret infinity, partial differential omega. For all n is greater than or equal to k, with a constant c independent of tau, h, and n. The proof of Theorem 2.2 relies on three crucial estimates, 5.6, 5.7, and 5.8, which involve the L-infinity norm of the finite element solution phi h and its derivatives. These estimates are expressed in terms of the L-infinity norm of the boundary data fh and its derivatives. The first estimate, 5.6, is proven by introducing the sector saint and employing lemma 5.1, which establishes the well-posed-ness of an elliptic finite element problem. This lemma provides an estimate for the L-infinity norm of phi h in terms of the L-infinity norm of fh. Relying on the weak maximum principle for the elliptic problem, 5.9, and the L-infinity stability of the L2 projection operator pH. The proof of 5.6 is completed by applying the triangle inequality and combining estimates, 5.10 and 5.11, yielding an upper bound for the L-infinity norm of phi h and its derivatives in terms of the L-infinity norm of fh and its derivatives. The subsequent estimates, 5.7 and 5.8, will likely involve similar mathematical techniques and arguments. The ultimate goal is to substitute these estimates into equation 5.2 to obtain the desired result in Theorem 2.2. The mathematical framework employed in this section involves elliptic finite element problems, L2 projection operators, and resolvent estimates. The use of the sector saint and the weak maximum principle are crucial for establishing the well-posed-ness of the elliptic problem and deriving the desired estimates. The L-infinity stability of the L2 projection operator pH and the resolvent estimate are also essential for completing the proof of lemma 5.1. The numerical solution of the discrete elliptic equation is obtained using the BDFK methods for k equals 1, 6. For n equals k, the solution UNH, 1 is determined by the discrete elliptic equation, which is solved using lemma 5.1 to satisfy the condition given in equation 5.6. This involves applying the lemma to the homogeneous part of UNH, 1 and utilizing resolvent estimates and L-infinity stability for the inhomogeneous part. Consequently, equation 5.6 is satisfied. For n is greater than or equal to k plus 1, the solution UNH, 1 is 0 for 1 is less than or equal to n is less than or equal to n2, and the elliptic equations 5.13 and 5.14 are employed to determine UNH, 1 and UNH, 1, respectively. The decomposition of UNH, 1 into homogeneous and inhomogeneous parts enables the application of lemma 5.1 to the homogeneous part, while the inhomogeneous part is addressed using resolvent estimates and L-infinity stability. This approach ensures that equation 5.6 is satisfied. The proof of equation 5.7 is established for n is greater than or equal to k plus 2 by extending GNH to be 0 for certain values of n and redefining GN1H and GNH. The solution UNH, 2 for n is greater than or equal to n plus 1 is obtained by solving a discrete elliptic equation. This involves a careful analysis of the discrete elliptic equation and the application of relevant mathematical techniques to determine the solution. The resulting solution satisfies the required conditions, thereby validating equation 5.7. The authors propose a generating function approach to analyze the BDFK method for solving parabolic partial differential equations. They define generating functions U, 2, zeta, and GH, zeta, as infinite series expansions of the sequences, UN, 2, and GNH, respectively. These functions are analytic in the open unit disk D and the complex plane C, respectively, for any h greater than 0 in P element of 1, infinity. A discrete elliptic equation for U, 2, zeta, is derived, a crucial step in the analysis, by multiplying the original equation by zeta n, summing up the results for n equals k, k plus 1, and using the identity and the initial condition UNH, 2 equals 0 for n equals 0, k1. The solution map of the discrete elliptic equation is denoted by mh, zeta, shish, partial differential omega, right pointing arrow shish. omega, mapping GH, zeta, to 2, zeta. Truncated sectors street theta and saint theta, sigma are also defined to establish the stability properties of the BDFK method. The authors recall lemma 5.2, which provides estimates for the generating function of the BDFK method. Specifically, for any epsilon and k equals 1, 6, there exists the element of pi, 2, pi, such that for any theta element of pi, 2, there exist positive constants c, c1, and c2, independent of tau, such that for all z element of saint theta, the estimate c1, z, is less than or equal to dt, e minus tau z, is less than or equal to c2, z, dt, e minus z tau, element of sp minus theta k plus epsilon, and dt, e minus z tau, minus z, is less than or equal to c tau k, z, k plus 1 hold. These estimates are crucial in establishing the stability properties of the BDFK method and will likely be used to derive further results in subsequent sections. The authors focus on improving the results of lemma 5.2 for the backward Euler timestepping method, BDF1, by introducing lemma 5.3. This lemma provides bounds on the function 1 caret, tau z, tau for z in the region saint, where theta is in the range, pi, 2, arcad, 2, pi. Specifically, it states that there exist positive constants c, c1, and c2 such that for z in saint, the inequalities, 1 caret, tau z, tau, is less than or equal to c2, z, and 1 caret, tau z, is less than or equal to c tau, z, squared hold. For sigma greater than tau, pi, the lemma provides further inequalities involving the function e caret, tau z, 1, z tau. The proof of lemma 5.3 relies on Taylor's expansion on a bounded domain and the fact that z is greater than or equal to pi, sin, theta. For z in GTH, sigma, gt, theta, sigma. By fixing an angle theta and a small positive value O, such that pi, 2 less than theta less than min, theta O, arcad, 2, pi, the authors establish the analyticity of the operator m, e caret, tau z, in the region street, theta. Using Cauchy's integral formula, they derive an expression for un, h, 2, which involves an integral over the contour gt, theta, sigma. This contour is deformed from a circle centered at the origin to a contour consisting of two parts, gt, 1, theta, sigma and gt, 2, theta, sigma, using the analyticity of the integrand and its periodicity in Im, z. The final expression for un, h, 2 is given in equation 5.23, which involves an integral over gt, theta, sigma of the product of mh, e caret, tau z, and gh, e caret, tau z. These technical results are crucial for establishing the convergence of the backward Euler timestepping method for a specific class of problems. The author's careful estimates of various functions and their derivatives, combined with the use of complex analysis techniques such as Cauchy's integral formula and contour deformation, provide a solid foundation for the convergence analysis. The globally continuous piecewise smooth solution U_H, 2 of the semi-discrete finite element method for the heat equation is decomposed into two parts. U_H, 21, the solution for T element of 0, T_N1, and U_H, 22, the solution for T element of T_N1, T_N. The Laplace transform of U_H, 2, denoted by U_H, 2, z, is expressed as the sum of the Laplace transforms of U_H, 21 and U_H, 22. The Laplace transform of the semi-discrete fem is derived by applying the Laplace transform to the variational formulation, resulting in equation 5.26. The Laplace transform of the piecewise linear function g_h, t, is given by g_h, z, equals e caret, tau z, plus e caret, tau z, 2, z squared tau, g_h, e caret, tau z, where g_h, e caret, tau z, is a function of the nodal values g_j caret h. This expression is obtained using the change of variables zeta equals e caret tau z, and straightforward calculations, as proved in lemma 5.4. The decomposition of u underscore h, 2 into u underscore h, 21 and u underscore h, 22 enables separate analysis of the solution for different time intervals. The Laplace transform of u underscore h, 2 provides a useful tool for frequency domain analysis. The closed-form solution for the Laplace transform of g underscore h, t, can be used in the analysis of the semi-discrete FEM. The results presented in this section provide a foundation for the analysis of the semi-discrete FEM for the heat equation, offering a framework for the analysis of the solution in both time and frequency domains. The authors of the research paper present a series of estimates and lemmas related to the solution of a homogeneous equation on a bounded domain omega. They derive bounds on the solution operator LH, E minus tau z, and the operator difference MH, E minus tau z, minus LH, E minus tau z. The estimate in equation 5.28 follows from Taylor's expansion and is used to rewrite equation 5.26 as equation 5.30, which defines the solution map LH, E minus tau z, of the homogeneous part of the equation. The authors then establish an estimate for the solution map LH, E minus tau z, in equation 5.31, which is bounded in the L infinity, partial differential omega, right pointing arrow L infinity, omega, norm. This estimate relies on the property of theta, given in equation 5.21, and lemma 5.3. Next, the authors prove lemma 5.5, which provides an estimate for the operator difference MH, E minus tau z, minus LH, E minus tau z. The proof involves a change of variables zeta equals E minus tau z and the use of elliptic regularity. The estimate is bounded in the L infinity, partial differential omega, right pointing arrow L infinity, omega, norm, and depends on the parameter tau and the complex variable z. The proof of lemma 5.5 involves the derivation of an equation for the difference VH minus WH, where VH and WH are the solutions of two elliptic problems. The equation is then inverted to obtain an expression for VH minus WH, which is used to establish the desired estimate. The L infinity stability of the operator pH is established through the resolvent estimate, lemma 5.25.3, and the mapping property of MH, zeta. This leads to the inequality, a nabla dl, mh, zeta, minus lh, zeta, fh, a nabla dl L infinity, omega, is less than or equal to c, z, minus 1 tau, z, 2, a nabla dl mh, zeta, fh, a nabla dl L infinity, omega, which further simplifies to, a nabla dl mh, zeta, fh, a nabla dl L infinity, omega, is less than or equal to c tau, z, a nabla dl fh, a nabla dl L infinity, partial differential omega. Consequently, the solution of equation 5.30 is represented as U, 2, z, equals LH, E minus tau z, E minus tau z plus E tau z minus 2 z 2 tau gh, E minus tau z, plus 1 minus E minus tau z tau minus increment h, minus 1 ph, 1 minus E minus tau z tau minus z, U, 21, z, plus 1 minus E minus tau z tau minus increment h, minus 1, 1 minus E minus tau z tau minus z, z minus increment h, minus 1 E minus z tn minus 1 2, tn minus 1. The inverse Laplace transform of U, 2, z, is then computed, resulting in the expression 2, tn, equals 1 2 pi I integral gdh, sigma U, 2, z, etn z dz. This is further decomposed into 4 integrals, each involving a different part of the solution U, 2, z. The first 2 integrals involve the operators LH, E minus tau z, and GH, E minus tau z, while the third and fourth integrals involve the operators pH and z minus increment h, minus 1, respectively. Subtracting equation 5.33 from 5.23 and using the boundary condition Gnh equals 0 for n is less than or equal to k-1 and n is greater than or equal to n-1, the expression unh 2 tn is obtained. This expression involves four integrals, each containing a different combination of the operators mh, e minus tau z, lh, e minus tau z, and gh, e minus tau z. The first two integrals involve the operator mh, e minus tau z, while the third and fourth integrals involve the operators lh, e minus tau z, and ph, respectively. The equations and inequalities presented in this section are crucial in establishing the stability and convergence of the numerical solution. The use of the resolvent estimate and the mapping property of mh, zeta, allows for the derivation of the L-infinity stability of the operator pH. The representation of the solution U, 2, z, and its inverse Laplace transform provide a detailed understanding of the numerical solution. The subtraction of equation 5.33 from 5.23 and the use of the boundary condition lead to the expression unh 2 tn, which is essential in analyzing the convergence of the numerical solution. In equation 5.34, a complex integral representation is presented, which is then broken down into three components: f_n_h, g_n_h, and l_n_h, as defined in equations 5.35, 5.36, and 5.37, respectively. These components involve integrals over the contour gamma_tau sigma, where the integrands contain various functions, including the exponential function, the Mittig-Leffler function m_h, and the function l_h. The first component, f_n_h, is derived by choosing sigma equals t_n in equation 5.35, and utilizing equations 5.22 and 5.28. This leads to an estimate of the L-infinity norm of f_n_h, which is bounded by a constant c_n cubed. Subsequently, the L-infinity norm of the sum of f_n_h terms is estimated, resulting in a bound of c max k is less than or equal to n is less than or equal to n2. G_n_h L-infinity partial differential omega. Similarly, the second component, g_n_h, is analyzed using equation 5.36, and the same choice of sigma equals t_n. This yields an estimate of the L-infinity norm of g_n_h, which is bounded by a constant c_n squared. The L-infinity norm of the sum of g_n_h terms is then estimated, resulting in a bound of c max k is less than or equal to n is less than or equal to n2. G_n_h L-infinity partial differential omega. The functions k_hs and q_h, defined in equations 5.38 and 5.39, respectively, are also integral representations over the contour gamma_theta sigma. These functions are used in the original equation 5.34 to represent the solution of the problem. The estimates obtained for the L-infinity norms of f_n_h and g_n_h provide bounds on the growth of these components as n increases. These bounds are crucial in understanding the behavior of the solution and its stability. The analysis presented in this section relies heavily on the properties of the Mittig-Leffler function and the function L_h, as well as the choice of the contour gamma_tau sigma. The estimates obtained for the L-infinity norms of f_n_h and g_n_h are essential in establishing the stability of the solution and its convergence properties. The mathematical framework employed in this section involves advanced techniques from complex analysis, including contour integration and the use of special functions. The results presented in this section provide a detailed understanding of the behavior of the solution and its stability. The bounds obtained for the L-infinity norms of f_n_h and g_n_h are essential in establishing the convergence properties of the solution and its stability. The estimates derived in the previous sections are utilized to establish bounds on the solution of the parabolic equation. Specifically, equation 5.41 provides an estimate for the L infinity, omega, norm of the solution, which is expressed as a summation of terms involving the L infinity, omega, norms of the solution at previous time steps and the L infinity, partial differential omega, norm of the solution on the boundary. By choosing sigma equals Tn1 in equation 5.37, and using the estimates in 5.29 and 5.31, a bound is established for the L infinity, omega, norm of the solution in terms of the L infinity, partial differential omega, norm of the solution on the boundary. This bound is expressed as an integral over the contour gth, sigma, gth, sigma, which is then estimated using the properties of the contour and the exponential function. The resulting estimate, equation 5.42, provides a bound for the L infinity, omega, norm of the solution in terms of the L infinity, omega, norms of the solution at previous time steps and the L infinity, partial differential omega, norm of the solution on the boundary. This bound is used to establish a recursive estimate for the L infinity, omega, norm of the solution. Furthermore, an inequality is established for the term 1e tau z, which is used to bound the L infinity, omega, norm of the solution operator kh's. This bound is then used to establish an estimate for the L infinity, omega, norm of the solution operator kh's in terms of the L infinity, omega, norm of the solution. The final estimate, equation 5.43, provides a bound for the L infinity, omega, norm of the solution in terms of the L infinity, omega, norm of the solution at previous time steps and the L infinity, partial differential omega, norm of the solution on the boundary. This bound is established by integrating the estimate for the L infinity, omega, norm of the solution operator kh's over the time interval, 1 taka, Tn1. The key mathematical concepts used in this section include the L infinity, omega, norm, the summation of terms involving the L infinity, omega, norms of the solution at previous time steps, and the estimation of integrals over contours. The estimates established in this section provide a foundation for the analysis of the solution of the parabolic equation in subsequent sections. The continuity with previous pages is established through the use of previously derived estimates and the application of these estimates to establish new bounds for the solution of the parabolic equation. The limitations of the estimates established in this section are not explicitly stated, but the assumptions used to derive these estimates are based on the properties of the solution operator kh's and the L infinity, omega, norm of the solution. Future work may involve the extension of these estimates to more general classes of parabolic equations or the application of these estimates to specific problems in physics and engineering. The authors focus on proving the main theorem, specifically estimating the error between the continuous and discrete problems. Utilizing the triangle inequality and theorem 2.1, they establish a bound for this error in terms of mesh size, time step, and number of iterations. They define an auxiliary function QH and prove it is bounded by the maximum norm of the discrete solution, leveraging the discrete Laplace operator and L infinity norm properties. This bound on QH is then used to estimate the error between the continuous and discrete solutions at each time step. The discrete solution at each time step is expressed as a function of the previous solutions, allowing the authors to bound the discrete solution at each time step using the previous bounds. Finally, they employ the triangle inequality and theorem 2.1 to establish the desired bound on the error between the continuous and discrete solutions. This bound is crucial for understanding the convergence properties of the discrete problem to the continuous one as the mesh size and time step approach zero. The weak maximum principle is a fundamental concept in the numerical analysis of partial differential equations, ensuring that the discrete solution does not exceed the maximum value of the initial and boundary data. This paper presents a proof for the weak maximum principle of semi-discrete and fully discrete finite element methods with k-step BDF timestepping method, where k ranges from 1 to 6. The proof employs techniques involving generating polynomials and the discrete inverse Laplace transform, also known as Cauchy's integral formula. A uniform time step size is required for the analysis, which limits the approach to k-step BDF methods and excludes single-step methods like Runge-Kutta or discontinuous Galerkin methods. The analysis begins by considering the generating function for the discrete solution, expressed as an elliptic equation with zero Dirichlet boundary conditions. The solution to this elliptic equation can be represented using the discrete inverse Laplace transform, involving a contour integral around the unit circle in the complex plane. By choosing a specific value for the parameter sigma in the contour integral, the discrete solution is bounded in terms of the maximum value of the initial and boundary data. This bound is then used to establish the weak maximum principle for the semi-discrete and fully discrete finite element methods with k-step BDF timestepping method. The proof is significant for the development of reliable and accurate numerical algorithms in various fields of science and engineering. The approach is based on the following key steps. Expressing the discrete solution as an elliptic equation with zero Dirichlet boundary conditions. Representing the solution using the discrete inverse Laplace transform. Bounding the discrete solution in terms of the maximum value of the initial and boundary data. Establishing the weak maximum principle for the semi-discrete and fully discrete finite element methods. The findings of this research have important implications for the numerical analysis of partial differential equations, ensuring that the discrete solution remains bounded and accurate. The authors employ the discontinuous Galerkin timestepping method with variable time step sizes, tau n, satisfying specific conditions. These conditions involve constants c, beta greater than 0, independent of the maximal step size tau, such that tau min is greater than or equal to c_tb, and a constant kappa greater than 0, independent of tau, such that kappa minus 1 is less than or equal to tau n plus 1 is less than or equal to kappa for n equals 1, n minus 1. Additionally, tau is bounded by 1, 4t. Under these conditions, application of the discrete semigroup estimates yields a bound on the L infinity, L infinity, omega, norm of the solution, which is proportional to c lane, t, tau, with an additional logarithmic factor depending on the maximal step size tau. The proof for the DG, 0, method is provided in the appendix and can be extended to the general DG, K, method using the approach from 20. The discrete semigroup estimates in LP, omega, are also presented, stating that there exists a constant c, independent of tau, such that the LP, omega, norm of the solution is bounded by the LP, omega, norm of the initial condition. The spacetime finite element space of degree 0 in time and degree r is greater than or equal to 1 in space. x0, r tau, h, is defined as the set of functions v tau h such that v tau h, in element of p0, Shay, for n equals 1, 2, n. The DG, 0, method for the homogeneous parabolic equation is formulated, and the proof of the weak maximum principle of DG with variable step sizes without the logarithmic factor is of particular interest and non-trivial. The discrete Galerkin, DG, solution, U_th, in x_0, r, is considered for the parabolic equation with a non-zero right-hand side f, where f_m is the L2 projection of f onto piecewise constant functions on each subinterval I_m. The DG solution can be expressed as a summation of phf_L, where pH is the L2 projection onto the finite element space sh. A parabolic equation with homogeneous initial and boundary conditions is then examined, leading to the establishment of the weak maximum principle of DG, 0, in Theorem A. This theorem asserts that for the fully discrete DG, 0, solution, UKH, there exists a constant c, independent of k and h, such that the L infinity, L infinity, omega, norm of UKH is bounded by the L infinity, L infinity, partial differential omega, norm of the finite element approximation of the boundary data, G_h. The proof of Theorem A involves defining the discrete harmonic extension, GH, of G_h, and considering the difference, VH, between the DG solution and GH. The semi-discrete problem satisfied by VH is utilized to derive the fully discrete problem satisfied by the difference, VKH, between the fully discrete DG solution and the L2 projection of GH. This approach enables the establishment of the weak maximum principle, providing a crucial bound on the fully discrete DG solution. The authors derive an estimate for the L infinity norm of the discrete solution VKH, M, using the properties of the rational function R and the elliptic theory. They start by applying discrete integration by parts to the summation of the product of the rational function R and the discrete solution GKH L, yielding an expression involving the discrete solution pH GKH L in the time step tau. By utilizing the properties of the rational function R and the elliptic theory, the authors obtain an estimate for the L-infinity norm of the discrete solution VKH M, which involves the L-infinity norm of the discrete solution GKH L in the time step tau. They then use proposition A to bound the L-infinity norm of the discrete solution GKH L, yielding an estimate for the L-infinity norm of the discrete solution VKH M. The authors then derive an estimate for the L-infinity norm of the discrete solution VKH M, which involves the L-infinity norm of the discrete solution G and the time step tau. They use the fact that the L-infinity norm of the discrete solution GKH L is bounded by the L-infinity norm of the discrete solution G, and that the summation of the product of the time step tau and the L-infinity norm of the discrete solution GKH L is bounded by the logarithm of the time step tau. The final estimate for the L-infinity norm of the discrete solution VKH M is given by equation A.10, which involves the L-infinity norm of the discrete solution G, the time step tau, and the logarithm of the time step tau. The authors also derive an estimate for the L-infinity norm of the discrete solution VKH, which involves the L-infinity norm of the discrete solution G and the time step tau. In this section, the authors delve into the discrete maximum principle for finite element methods in convex polyhedra. They establish a discrete maximum principle for a class of finite element operators, which is essential for ensuring the stability and accuracy of numerical solutions to partial differential equations. The discrete maximum principle is derived using a combination of mathematical techniques, including the application of the triangle inequality and estimates on the eigenvalues of certain matrices. The authors also utilize results from previous studies on non-obtuse simplicial partitions and discrete maximal regularity for finite element operators. The main result of this section is the establishment of a discrete maximum principle for a specific class of finite element operators, with an emphasis on the importance of maintaining the discrete maximum principle in finite element methods. This principle plays a key role in preserving the positivity of solutions and ensuring that the numerical solutions are physically meaningful. This research paper presents a comprehensive list of key findings and methodologies in the field of computational biology. The study focuses on the development of novel algorithms for protein sequence alignment, which is crucial for understanding evolutionary relationships and functional similarities between proteins. The authors introduce a new algorithm, named Pro-Align, that significantly improves the accuracy and efficiency of sequence alignment compared to existing methods. Pro-Align utilizes a combination of dynamic programming and machine learning techniques to achieve better results, especially when dealing with large datasets or highly divergent sequences. One of the significant contributions of this work is the development of a scoring function that effectively captures the complexity of protein interactions. This function takes into account not only the identity of amino acids but also their spatial arrangement and potential interactions, providing a more nuanced understanding of protein relationships. The paper also discusses the importance of considering the evolutionary context during sequence alignment. By incorporating phylogenetic information, researchers can better understand the history of protein families and identify potential functional shifts or innovations. In terms of technical details, the authors provide a detailed description of the algorithms used, including pseudocode and computational complexity analysis. They also present an extensive evaluation of Pro-Align's performance using various benchmark datasets, demonstrating its superiority over existing methods. Limitations of the study include the need for further refinement of the scoring function and the potential for bias in the training datasets. Future work could involve integrating additional types of data, such as structural information or functional annotations, to further improve the accuracy and utility of protein sequence alignment algorithms. Overall, this research contributes significantly to the advancement of computational biology by providing new tools and methodologies for understanding protein evolution and function.